He is David LACEY. He is working as the designer and the director of the software development part for all those software kits that assist engineers in the creation of the best machine learning on top of the graph core solution. As a processor, they have IPUs, which is the intelligence processing unit. I'm sure he will talk to you about this. So without further ado, hi, David.
Hi, how are you doing? Thank you very much. So, hi everyone, and thanks for letting me join this conference. And I want to talk today about accelerating machine learning model deployment with IPUs, with the processor that Graph Core provides. So, oh, hang on, just need to get my slides going. There we go. So what I'm going to talk about today is, initially, I'll talk a bit about machine learning deployment, what it means, kind of what the major concerns are, what we care about when we're doing deployment phase of a machine learning project. Then I'm going to talk a bit about Graph Core, the company, and the IPU and the product we provide. So I'm sure people are interested in, and people might not know about our products. So I'll talk a bit about that. And then particularly for deployment, that's where we get into the realm of scaling to very large systems. So I'm going to talk a bit about large scale deployment. How do we deploy an algorithm on lots and lots of IPUs, talking hundreds and thousands of chips that you want to run your program on. So starting with the deployment aspect. So here I have a very basic, simplified down life cycle of what a project's like. And there are lots of intricacies and lots of variations on project workflows. And that's not really what this talk is about, but it's good to think about it to start with. But most of them will have an initial development phase where there's a lot of iteration and we're creating the program that we wish to deploy. And then a deployment phase where it's actually going to be put in the final product. And everything's a cycle. So we will go around development several times and then into deployment, but quite often we'll go back into development again and the program will be updated and so on. So these are quite interleaved. But as I say, for today, I think there are some very specific concerns we have with the deployment phase. And that's what I want to look at. So what characterizes deployment? Well, at this point, I mean, the big thing is that we're actually using this program or machine learning model in the end product. It's out there being used with your end users. And to do that, we have some degree of stability in the model or the algorithm. There might be some changes, some online changes, even in the deployment phase, what happens in that model. But usually we fix what it is, which allows us to do more in terms of checking for reliability and optimizations on that fixed program. In these cases, I'm talking really about either inference or training. And in both cases, we might well be running on a much larger set of compute resources, which is why I'm going to talk about scale out later. Either in inference, we've obviously now addressing the user base of the end product. So we need lots of compute to address the requests for inference that occur there. Or in training, when we are dealing with our final deployment for our final data set, then we need a large amount of compute, and I'll talk a bit about that later. And often then, during this phase of the project lifecycle, actually we'll have a totally different set of people working on it. This will vary from company to company, but particularly in large companies that we're working with, we'll actually have a totally different team of engineers working on the deployment phase of a machine learning algorithm that work on the development phase. Obviously, they talk to each other and there's a lot of iterations, they say. Can vary a lot. And in fact, all the things I'm saying here have to have the prefix generally. There's a lot of variation in kind of what constitutes deployment, what we mean by it and what properties it has. But in general, this is the area I'm talking about when we have these kinds of properties. Okay. So if we think about that phase, I think often the way we think about it here, and I tried to break it down into a couple of axes here, is the things we worry about, the areas of concern, and then we'll have, for the different levels of implementation, kind of what that means. So under the things we worry about, a very big area of concern at this stage is cost. Probably a bit more than development time, is that we really want to cost optimize our deployment at this point because of the large scale resources we're using. Clearly, we care about application quality, and that is true in development as well. But then other aspects of quality of service, application quality come in. Reliability, how often do we have errors? How do we deal with errors? Transparency, kind of what information can we get back from the deployment? Flexibility, how can we deploy this on different systems in what different ways? And then obviously security as well becomes, again, probably more of a concern in the deployment phase of a project than in the development phase. And then the other axis we have are the levels of the implementation. So we have the algorithm itself, where we're thinking about what the model structure is, what the data set is, what the optimizer is, that kind of thing. The software implementation, what framework are we using, what libraries, what drivers, and so on. Then we have the system and the infrastructure software. So both the networking infrastructure in a data center, the OS, and so on. And then finally, the hardware at the bottom. So we think about these two axes of our concerns, we end up with a grid of many, many things to worry about. And at GraphCore, we do worry about all these things. And we can see that if you kind of dive into any particular entry in this grid, you'll find a different thing that needs to be dealt with. So deployment is a very complex thing that we have to deal with. And our aim at GraphCore is to try and provide a platform of hardware and software that allows you to handle all these issues in a very easy way. For example, if we were looking at the application quality at the algorithm level, we'd be thinking about what's the percentage error rate we have in our model, how does it generalize, kind of what happens, are we applying the right data set, how is that going to evolve over time, and so on and so on. But as you go down the stack, you might be thinking in the implementation part of the stack about floating point errors, about floating point range, and then you might be thinking about quality of service metrics like kind of how quick is latency, what's my balance between latency and throughput and inference, and so on and so on. So across a whole range here, we have many things to think about, and I don't have time to go into all of these. I just wanted to point out the kind of the vast range that we have to deal with in trying to put together a complete machine learning solution. And some of these things are very specialized to machine learning, artificial intelligence, and some of these things are more kind of just general, kind of any deployed software application, you would have these concerns, particularly a data center high performance scaled out application, which is what a lot of machine learning applications tend to be. So that's where what we're thinking about. And GraphCore, the company I work at, is trying to provide a solution to address this well, not just trying, but actually succeeding, in my opinion. So I'd like to talk a bit about GraphCore. We've been around for about 5-6 years now. We started in the UK. Our headquarters are in Bristol, where the majority of our engineering are. And we now have grown to about 450 employees worldwide, and are addressing many kind of machine learning and artificial intelligence kind of workloads and customers around the world. I'll just point out here, obviously, we are still hiring. We are expecting more growth this year, particularly looking for more software engineers, silicon and system engineers, and so on. So kind of if you're interested in that kind of area, then do get in touch. But what we actually do is we produce hardware and software for artificial intelligence and machine learning. So at the core of that is the IPU processor, a processor we designed from scratch, particularly for artificial intelligence and machine learning workloads. But producing the innovative processor is only half the work, really, or less than half the work, really. What you need to do on that is then build a full solution that people can use for real machine learning. So key to that is the software. That's kind of my area with that. And we produce the POPLAR software stack, which is key to kind of really efficient and easy development of machine learning on a new efficient computer architecture. And then we scale it out to the platform level. So I'll talk about the IPU-2000 and how we can scale this out to hundreds and thousands of chips. The M2000 is a single unit server box shelf with 4 IPUs on. That in that one unit gives us 1 petaflop of IPU compute. So it's a very high performance compute platform, and it also has a very high performance communication fabric for tying these together, up to 2.8 terabits per second of communication bandwidth in the box. And this is the key product. This we launched and was shipping at the end of 2020 last year. And I'll talk a lot more about this box when we get to the scale-out part of the talk. That's basically what GraphCore provide. And we can build that up and up and up to make really big systems. So at the bottom, we have a single processor. If we put 4 of those into an IPU M2000 to give us a petaflop of, when I say AI compute, this is 16-bit floating point precision with stochastic rounding as well, which is very important for the world of machine learning. Then we can put 16 of those together in a single rack, which is our POD 64 platform, which gives us 16 petaflops of compute. And then we can connect up to 1,000 of those together, potentially, to give us up to 64,000 IPUs, which would actually, if you build a system that big, no systems that big exist today, it would be 16 exaflops of compute. At the bottom of this is the Colossus Mark II processor. This is our 2nd generation processor. It's big. It's 59.4 billion transistors, which makes it pretty much the biggest chip made today. What we've used that space for is to put a large amount of compute units, which I've already talked about, and also a lot of on-chip memory. So on a chip, we have 900 megabytes of in-processor memory. So this is actually on the chip itself. And then the compute is arranged in a very highly parallel fashion. So we have about 1,500 cores, which are split into threads. So it gives about 9,000 hardware threads of parallel compute, which does all the work for computing a deep learning model, for example. This is a big thing for us. This is about an 8 times step up from our previous Mark I chip and provides the basis of our machine learning workloads. Here I've got the inside of the chip. I won't go into a lot of details here for time, but you can see there's 1,500 processors. They all work in a BSP fashion, so they all work independently on their own distributed data memory. And then in the middle there, you can see a very, very fast communication bus. So within the chip, we have a lot of communication between the cores to exchange data between the cores. And actually we have an 8 terabytes per second all-to-all exchange. So it allows for very flexible data communication patterns within that chip. And I say this allows us to do very kind of high performance workloads, the kind of things you get in deep learning. So kind of computer image, classification, object detection, language processing, that kind of thing. Okay. On the M2000 itself, we put 4 of these, and then we add a gateway chip, which does communication, which I'll talk about because it's key to scale up later on. But here I'll point out that we then can extend it with external memory, external DDR on that box. So we can actually have up to 448 gigabytes of external DDR memory on the same box as 4 of these IPUs, each with 900 megabytes of in-processor memory. So we get a really nice balance for compute here. We get a large amount of very, very fast to access in-processor memory, and then we get, which gives us high compute, and then we get capacity. We get a very large amount of off-chip memory to give us the room to store very large models, for example, which is very key to machine learning nowadays. On top of this, we have our POPLAR software stack. So this is our SDK, and this is actually an area I work in quite a lot, but but I don't have the details to go into how this ties into the development cycle. But I think the key takeaway is we've done a lot of work here to optimize to get the best use of the chip, whilst making it very integrated with standard development frameworks that people use. So the challenge here is to say, how do we kind of take that very highly parallel processor and then just kind of make it work for someone who's written, say, a PyTorch model or a TensorFlow model or something like that. And that's what this SDK does. And that's where we put a lot of our time. And now it is a very nice user experience that you can just write your models in TensorFlow and PyTorch, and it will compile it down to using our POPLAR graph compiler, we'll compile it down to run on our chip. Okay. Actually, if we think about the grid I was talking about in deployment earlier, you can see actually that the SDK deals with both the application quality, the reliability, actually transparency as well. I have to apologize, my slides are slightly out of date here, but and flexibility at the ML algorithm and software implementation level. So that's very much where our SDK kind of spends its time thinking about in that grid of concerns I had. And what it gets us is very, very high performance. So that development SDK and what it's designed at is very much saying we're going to take this high performance chip and for a particular model, say EfficientNet or BERT for language processing or something like that, you can actually get the kind of throughput and latencies that are best in class, that kind of are better than any other competing chip out there. And I'm not going to go through the benchmarks today, but I put a link on the slides here so people can see that actually across a lot of industry standard benchmarks, we have a very, very high performance competitive platform. Of course, what that translates to in the deployment sense is cost reduction, but also application quality, because there are levels there where you can only get the latency of inference that you need if you've got the kind of performance from a low batch sizes, for example. Okay, so that is a very kind of brief tour of our base product. We have a highly parallel chip. It's very high performance. It produces kind of takes standard models and lets you run them in a very efficient way. But then we want to take what we developed there and then deploy it on a very large system. So we have to think about scale out. And when we think about scale out, I'm going to talk now a lot about the hardware part of it, actually the system part of it, because that's key how we put those together to get the kind of flexibility we need. And we're very concerned about cost and reliability and flexibility at the system infrastructure and hardware level. So I'm going to show you how we've done that at GraphCore. And we need to do that because either for inference, you might be serving a lot of customers, but even for training, there's been a real drive recently for very, very large models. You can see that in language models, which I've got here, which as well as needing the very high capacity of memory and so on, it also is going to need a lot of compute. So you're going to need a lot of processors to actually kind of train these things. So there's a big demand for very large models and very large compute infrastructure. So if we're going to deploy our training onto these large compute infrastructures, we better do it in a flexible, easy, cost-effective way. Key to it at the bottom, as I said before, is the M2000. How is that unit actually made up inside to allow us to do this good scale out? Well, we have 4 IPUs. We then have those are then powered by custom power supply units, 2 of them together, and an advanced cooling system we developed. The main it looks very pretty, I think, there on the left-hand side. And the main reason for kind of developing that cooling system is to make it compact, to fit all this into one new rack, which gets us very good density in the data center. Connecting those IPUs to the rest of the world is this gateway SoC, which actually has an ARM processor on it, and also then has custom hardware to do basically communication routing for getting the various communication fabrics to talk to each other. And those will come out via a smart NIC connector, which will allow you to connect a custom NIC for the data center together, as well as various ports for our custom interconnects. And it will also connect to memory, which is just another communication fabric, if you like, to the DDR4 memory, which I talked about, to get us that large capacity for doing large models, kind of algorithms that need a lot of memory. So this gateway allows us to connect these IPUs over 4 main interconnects. We have IPU links, which do IPU to IPU data communication. We have host links, which means connecting the IPUs to a CPU, to a server, which is running computation. We have our gateway links, which does cross-rack data communication. And then there's a PCI bus, which is the standard way you connect to memory. So the gateway chip kind of connects 4 different communication fabrics. The first one of those is I'm going to talk about is the host communication. So we have something called IPU over fabric. So if you imagine an accelerator, some other accelerator cards, they're a PCI bus, so you have to put them into the same chassis as the host, the CPU, which is fine, but it kind of damages your flexibility and your ease of kind of integrating into infrastructure. So what we do is instead we separate that over Ethernet. So the IPUs connect to the gateways connect over your standard data center Ethernet to the host servers. And that can be 100 gigabit Ethernet or InfiniBand or whatever your standard data center is. And that allows us to do disaggregation to separate the idea of what the host is compared to what the IPUs doing the AI compute are, the regular compute to the AI compute. So then, bearing that in mind, we can then map out exactly how we put these things together. So within a rack, we connect 64 IPUs via these custom IPU links. Now, IPU links are dedicated software managed, unswitched links that kind of do the things like the sharing of gradients during machine learning training or something like that. They're very efficient, targeted at very low latency efficiency and software management, under software management. The gateway will then connect to our standard Ethernet fabric for IPU over fabric, as we've said, which connect to the disaggregated host servers. And then we put several racks together, which are then connected via our gateway link fabric, which is also a switched Ethernet fabric, but it's separate to the one used by the host as well. This allows us fast communication and so on, but a lot of flexibility between racks. On top of that, you can also attach network attached storage to this fabric. So that gives us a whole picture of how these things are connected together. Here I have a very specific 512 chip system just to show all that with all the top of rack switches in and so on. Note that that disaggregation I talked about means that we can connect our host servers either on the same rack as those IPUs, or they could be separately in our data center. It doesn't matter, and that gives us that flexibility that I'm talking about in that way. Okay, so that's basically how we build these things up, and we just can keep on going until we get very large systems. Now, to build on top of that, to show the flexibility of that system infrastructure that we're talking about, because that's what we're about today, we have to add more than just a development SDK in terms of software provisioning. What we have to have are a resource management software platform, so something that allows us to allocate which parts of this big machine are being used by which users for which applications. And also we need a good hardware management and monitoring, which we do via pretty standard infrastructure software like Prometheus, Redfish, and Grafana. So when we do that, we can imagine several different scenarios. You need that because different people deploy in different ways, where either we kind of totally pre-configure what we want, or it's kind of managed by an administrator, or so on and so on. What this allows us to do is split up our compute in many different ways. So here you can see in this diagram, the different colors represent a different set of IPUs applied to a different application. And this is the kind of flexibility we need. We need to say, well, in this case, this application is going to have 4 IPUs here and 8 IPUs here, or sometimes you might want to then reconfigure and do it across 128 IPUs or 512 IPUs. Now, the resource management software we have allows you to either do that upfront by an administrator and pre-configure it to be set, or it can be dynamic. So every job can reconfigure which IPUs are logically connected to which host server and which application. So it gives us a lot of flexibility, which is really what you need for large-scale deployment. This can be done either in a bare metal way or via kind of VMs and containers, and then we can build orchestration on top of that. So imagine you have a job manager like Slurm. If people are available that, then you're going to say, well, I want to kind of now run this job for the next few days, which is going to serve this this particular application, and I wanted to run over 128 IPUs. The job scheduler itself can then wait until there's free resource. It can contact our resource management software, which will then allocate which IPUs are connected to which server, and then it can run the actual job on that server. So we have a lot of flexibility. This also allows for quite clever stuff like migrating workflows and things like that. We could do exactly the same with Kubernetes as well. So there's a real need at this kind of level to run efficiently to actually kind of build up your software provisioning and use standard orchestration software and so on. Now, when you divide up these IPUs in deployment to be used for a big training job, then they'll need to communicate with each other, and so we have to use this kind of flexible interconnect we've got to do many axes of collective operations. Collective operations that tend to come up in machine learning are things like reduced scatter patterns and all reduced patterns and things like that. So you're sharing information and then trying to get that information averaged and spread back along the compute units, basically. So we've split up these IPUs. We have to do these collectives. What you really want is then it to not affect your application quality or cost. So you don't want those as you get bigger or smaller or divided up in different ways. You don't want those operations to get slower or faster, particularly. You want them to take the same amount of time so you can predict you don't get a damaging kind of performance penalty. And that's something else that we've worked quite hard on with our collectives library called GCL in the POPLAR stack that says that as you get more and more IPUs, the actual time it takes to do one of these data sharing operations is the same, it's constant, which means you kind of get linear scaling on your applications. So overall, this provides a kind of pretty standard way of integrating these very large systems in a very flexible way into a standard data center IT system. And that's what we really need to address a lot of those concerns I talked about in deployment. Just a quick talk about then how we kind of build that up. We've actually kind of used this standard infrastructure to allow us to build out a partner program with several other providers to allow us to provide these solutions for deployment to people, and that allows you to go and use it. One other thing I'll just want to talk about before we get to the finish, and that's another aspect, which is transparency. So this is actually, as a software architect, is very interesting to me, is that I've talked a lot about the cost and mobility and flexibility of our systems there, but another aspect we need to think about is transparency. How do I know what's going on? And another thing, which I don't have time to go into, but I will just kind of point at a bit, is that we've done quite a lot of work on different software provisioning, and I think anyone who's doing this kind of work needs to, in providing good analytics, both at the application level, so how much is like each individual part of my application taking, how much is the communication taking in terms of performance, where are the errors happening, what's the allocation currently, what's the job utilization, et cetera, et cetera. So we actually have to put a lot of effort into, for efficient deployment, we have to put a lot of effort into actually good metrics and error reporting as well. So in summary, deployment's a hard business. There's a lot you have to think about. I tried to give just a very brief talk today of the kind of things we're doing at Graphcore and the ways that we kind of try and build a very easy to use but very flexible and efficient deployment platform for machine learning and artificial intelligence workloads that people can work with. If anyone's interested in this, the MT1000 product I talked about is available now. We kind of launched it last year, and it's been shipping since before Christmas. We have that partner network I talked about, which allows, which kind of specialize in the scale out part of it. Kind of as you put your data centers together, you can buy the systems from us, but there's integration to do. And then you can either contact directly our sales team at the email address there, or there are a couple of web links here which kind of give you information on either the partner network or more information about the technology. And I'd encourage people to go there. So I think that kind of hopefully gives a very quick tour of deployment efficiency and what's needed in that area. and how GraphCore provides for that. Thanks very much.
Thank you, David. It was sharp on time and a very good talk. Thank you. I encourage the audience to give their opinion on the talk in the poll before we start with the Q&A, and to please write as many questions as you want, since we have 15 minutes, so we should profit from this time to have as many information as we can grasp from David. In the meantime that we are waiting for questions, maybe I will do some apocryph questions. As a disclaimer, I'm not an hardware expert, so I will make software-based questions only. To start, maybe if you would like to tell us something about the analytics, what you just mentioned. So what is the work you're doing within analytics?
Sure. So let's start at the kind of application level. We have something called the way the POPLAR SDK works actually is by doing kind of whole graph compilation. Which is so it knows about the whole machine learning program up front. This allows us to actually have a really good view of static analysis information, as well as being able to add instrumentation automatically to kind of profile on the chip. That gives us then kind of profile information, which can be kind of gathered back from your deployment, and then it gets fed into a graphical analyzer called PopVision application viewer. I'm sorry, that's not quite right name. Sorry, the graph analyzer, and and that shows you a lot about down to like kind of this matrix multiply is taking this many cycles, this all juice is taking this many cycles and stuff like that. So that's one aspect of it. Moving up a notch to like the application level, but not kind of the level that's running on the chip. We have something called the PopVision system analyzer. Now, what this does is it adds information points at the kind of more the system level. So the host application there's actually a library where the user can do it themselves called the LIFECYCLE, the PopVision visualization and tracing instrumentation library, and that allows and it's built into our stack as well. So that will tell you, for example, in a data feed, kind of how often. Kind of the events that happen when like feeding stuff over the network, kind of when the application runs, when it finishes, and so on, and that could be aggregated over many compute nodes and brought together into a similar kind of visualization. So that's the second part, and then the third part is the virtual IPU resource management system has a kind of visualization you see, so you can see exactly which IPUs are allocated at which times, and it gives you that information. And then finally, we have and that's all kind of automated from the central kind of resource management server. And finally, we have kind of, as I said, pretty standardized hardware monitoring system. And once you get to the level of like how many erroneous Ethernet packets have I had, kind of what's the power measurements, things like that, you want that to be very kind of standard infrastructure. So that's again where we kind of just make sure that we plug well into the kind of most popular third-party things out there, like the Prometheus, Redfish, Grafana stack, and so on. So kind of it's almost across those four levels that I talked about.
Yeah, of course.
We have like different visualizations.
Yeah, from all four levels, probably the most interesting for me is the virtual IPU level, and I guess.
Right. Yes.
You're using the live profiling to feed back to this level as well, so to change the way you are configuring the allocation, or it's maybe possible to do so?
No. It might be possible in the future. For example, at that level, we can. At the moment, it's very user directed. So, kind of, you say exactly, I want this number of IPUs for this job or whatever.
On demand.
We actually. There is possibilities to link them in the future, but at the moment we want good predictability for the user. So the kind of future innovations you could do in a system like this would fit in really nicely, but I don't want to give too much away. Is, for example, you might actually, when we have control all the way up and down the stack under kind of user control, you can actually kind of balance off deep learning training, for example. You've got to balance off between the number of IPUs you take, the batch size per IPU, and the learning rate, and so on. And you can actually kind of tie this stuff together, so you can actually decide the same job depending on your performance constraints and your resource constraints, exactly. You can do the same job across different numbers of chips, and that's the kind of like intelligence you could put into that layer.
Yes.
At the moment, to say we don't, because it's better to have user control first.
Yeah, of course. I see your point there. I have here a question from Peter, or Peter actually, because I think he's Hungarian. If you could address the reliability and the energy consumption issue, so from the whole system perspective, I guess.
Yes. Reliability with respect to energy consumption, or kind of just two of them, I suppose. Really, yes. So the majority of power in these systems is taken by the compute units, by quite a way, and generally energy kind of just relates to what your power efficiency is. Actually, it's not. There aren't kind of as many kind of clever little things there as much. One thing that so actually kind of getting our benchmark results are kind of saying in some ways that our power efficiency is good, which means our overall energy usage is good as well. I think one of the things that kind of bodes well for graph-core IPUs in terms of energy efficiency is the memory architecture, because by putting a lot of memory on the chip, and this has to be done from the chip kind of very, very kind of fundamentally at the chip level and then built upwards, by putting a lot of on-chip memory where the distances are very small, basically, you don't spend as much energy kind of moving data around up to that 900 megabytes limit. And actually what that allows you to do is it allows you to have in fact, a slower memory bus to DDR4 than if you kind of didn't put as much memory into the chip, but still get the same performance. Now that, in the end, gets better power efficiency because you're not spending as much time, as much energy on a very fast memory bus, kind of moving in and out of external memory. So that's part of the kind of architecture design, if you like, of the chip.
Okay, thank you.
In terms of
let me see, because I have some funny questions, maybe to break a bit the seriousness of this last answer. Adam asked if you're not afraid that Bitcoin miners may flood your market, similarly to what happened to the GPU market. Will they all steal your product?
Well, it's a question we get all the time, actually. It's can you do cryptocurrency mining on this thing? I would say that actually it's not designed for that, unfortunately. Well, maybe fortunately or unfortunately, depending on what your view is. It's very much designed from the ground up for machine learning. I don't know if anyone's tried, but it's not really centered around integer performance as much as you would do for cryptocurrency mining. But if I had Bitcoin for every time I've been asked to, I'd be richer every day.
Maybe you wouldn't be here talking with us if it was that easy. Okay, less funny, I hope less funny question maybe, whether you have any projects in your company related to the security tool sets, because you didn't mention them. If not, because it's not your area of...
No.
No?
So only in the respect that we try not to break any external constraints on security.
Okay.
If you want to put these kind of things on cloud, the way I've been talking today has been as a lot about kind of as if you're doing an on-premise system, but actually the other way we deploy these is on cloud. Infrastructure. We had things on Microsoft Azure, for example, and there are a lot of security constraints. So it's about fitting in with an external cloud providers, for example's security constraints, and not breaking any. That's the first thing. Yeah. There are more things that can be done in terms of encryption and things like that, which might be a direction in the future, but I can't really talk about them.
Okay. We won't force you. Let's keep it secret for the next year, maybe. Instead, maybe you can also tell us something about the partner group you were mentioning, and maybe if you want to make some examples, since in 2020 you already had some first deployment, so of how in real life the product is being used.
Yes. So these partners are all more kind of service provider partners that we work with. For doing kind of integration work and so on. And we work both through them and directly. We have got, I can't emphasize now, there are various kind of customer stories on the website, which excuse me, my slides are automatically moving. I'll put it there. Rather than me misremembering them and misquoting people, I'll just point them towards a website where there are some customer stories on that. There are a wide variety of what we do, and it varies quite a bit between research institutions and large hyperscaler deployments and so on and so on. And some of those we work directly with and some through these partners. So it's a bit hard to give the scope here. I think it might be better just to point people towards that. Yeah.
Okay, thank you. We have probably time for another question. This is from Peter. He asks whether and how would you detect then the failed units among this huge number of very good properly working units? So, because you showed something very complex that said can be also distributed.
How do we detect failed units?
Yeah.
Was that the question? Yes. So this is done via the board management controller, which I kind of skipped over a bit on the things. And then again, it's kind of standard infrastructure for doing that kind of thing. And I'm going to be totally honest here, not really my area.
Okay. Sorry.
Be developed or whatever. But it's from what I understand, it's the key there, like in some of the other things like the security, is to be is to make sure that you can integrate with standard infrastructure. No one wants a custom hardware failure detection infrastructure, right? Everyone just wants it to be what they're using in their data center anyway. So that's the key. The key is to be make sure that you kind of obey standard protocols and can be or have the hooks to go into standard IT infrastructure.
Which I guess is the usual story with hardware. You just need to be compliant to make everybody happy.
Yes. You want to be as seamless, both in the software and hardware. There's a balance actually between innovation to get like value, to get like it running faster or whatever, and standardization and seamless integration into infrastructure to make sure that you're not having to spend too much development work or kind of systems admin work to get that together. And we try and make sure we explicitly kind of decide where we're innovating and where we're trying to be kind of as standard as possible.